is Aryeh. I work for Xslt Solutions. Xslt Solutions is a company that focuses on helping clients with their content, with their information. We help anywhere in the information cycle that anyone needs help. We help anywhere from information design to conversions, to style sheet work, to XML, to single sourcing. Here's just some of the customers that we've had. And on to today's webinar. We're going to be talking about performance in the DITA OT. As usual, please ask questions, or as usual, I ask everyone to please ask questions. In particular, in this particular webinar, I'm not sure if the material is targeted to the audience that's here, so if anybody feels that I'm going too fast or too slow, please let me know. So, an introduction to what we'll be discussing today. We're going to be talking about performance in the DITA OT. We'll be talking about all parts of the DITA OT, starting from the different vantage points, from talk about hardware and software and your own customizations to the DITA OT. And just by way of introduction, the first thing to tell everyone is that I have no easy answers. There is no magical switch that you just turn on and therefore your DITA OT processing goes really quickly. A lot of people are suffering from slow DITA OT processing, and I don't have any great answers for that performance problem. I will be talking about different strategies to mitigate the problem and things that might be able to fix particular performance problems. But I don't have any easy answers that just simply makes the DITA OT fast. So the DITA OT, much like many areas in software development, there's no silver bullet to the challenges. There's no easy way to make the DITA OT run fast. So before we start talking about what to do about it, I just want to point out that the DITA OT itself is designed in a way that isn't really designed for performance. DITA OT is designed for correctness, for features, trying to make sure that all of the DITA OT specification works. I'm sorry, that the DITA specification works. The DITA OT is just one implementation of the DITA specification, and the specification doesn't necessarily track the DITA OT precisely. The DITA OT is designed in a way to try to make sure that that we can implement it correctly. It doesn't have a huge team behind it. It's not like Microsoft Office or some project that has hundreds of thousands of developers. So we want to be sure that first things first that we get correct output, and then if we can get all of our bugs fixed, then we'll start worrying about performance. And because of that, that means that practically speaking, we have a tool that isn't that fast. So that being said, there is work that is underway to try to make the DITA OT faster. We'll discuss that briefly as we get underway. So that's the basic problem of performance with the DITA OT. Another point that we need to make when we're making our introduction is that when we discuss performance, it is important to discuss what we mean by performance. After all, it would be handy if the DITA OT processed, a 1,000-page book in a second or two. But for many purposes, no one needs that. A lot of people need performance that fits with their workflow. They need performance that enables them to get their documents ready and published in the time frame that they have, but that might very well allow 5 minutes for a document to publish, and that won't cause anyone to have any problems with it. Whereas if a document takes 3 hours to publish, then that can really mess up people's day. So when we're discussing performance, part of the issue to keep in mind is that we're going to be talking about, do the performance issues that we have cause us problems or not? Because we always need to consider how much time and energy we're going to spend on addressing performance issues. So easy performance fixes we'll always want to take care of, but if things are more complicated, they require a significant redesign or significant investment, then we start to need to think about exactly how much performance we need and how much is worth spending to get that performance gain. So every time we discuss performance, we want to discuss it in the context of saying, well, is this going to be a significant advantage or a minor advantage, or is this something important and worth the trouble, or is it something that's not really worth it because, frankly, we'll save 3 seconds and nobody will care. And the final note that I wanted to make by way of introduction is that there are simply no hard and fast rules that I can give to say you need to make this one change, and this change will speed up your processing. Practically speaking, every change you make will have a different impact depending on your precise setup. If you have a copy of the DITA T on one computer, it'll behave differently than a copy of the DITA T on another computer. And if you have one kind of data set, you're going to have different kind of performance than if you have a different kind of data set. If you use lots of conrefs, then my data has many different cross-references. It may behave differently. So in every case where performance is concerned, I can give general guidance, but everyone's case is going to be slightly different. Their data, their customizations, their particular environment will affect their performance. So if anyone wants to make sure that their processing is fast, they are going to have to test using their own data on their own system, and they'll have to measure and see what works best for them. Okay, the outline of how we're going to go through this, we're going to talk about some of the performance pain points in the DITA T itself. We're going to talk about hardware and software changes that can affect performance. We'll talk briefly about memory settings for Java, and we'll talk about style sheet performance and code changes that you can make in your style sheets to speed up your processing. So as I alluded earlier, the DITA T by design sacrifices speed for simplicity. As I've mentioned in previous webinars, the DITA T is constructed as a pipeline. It's a series of steps. Each step is designed to do one thing and one thing well. What that means practically, though, is that computations that you might have had to do once may get repeated many times, and therefore the processing as a whole will be slower. So one of the particular pieces of computation that has to happen repeatedly is that every step when we're going to read our DITA T files, we're going to have to parse them. And that involves taking the text and figuring out what's the character. It used to be in the days of ASCII that it was pretty simple. A byte was a character. Nowadays, we save our files in Unicode. And in Unicode, even figuring out what's a character is not completely trivial, because the character might be 1 byte, or it might be 2 bytes, or 3 bytes, or more. And because of that, that means that just the simple act of reading a text file takes some computation. So if you have to reread a text file many times instead of reading it once, you're going to have to do extra computation. So because the model of the DITA is to reread these DITA files repeatedly, so we're going to have to pay the price of reading Unicode text files. Then on top of that, we're going to have to pay the price of constructing the tree of the data from the XML. In other words, that you have parent elements and child elements, and each element has attributes, and each element has children, which may be text or comments or processing instructions. Constructing that tree in memory has a certain performance cost, and that's going to happen each time after the file is read before we do anything with it. So that means that when we're going to be processing each file repeatedly, we're going to have to pay the price of parsing the file many times. Each time when we open a DITA file, we might have to read more than the file itself. When the file has a doc type, and all of our files should start with a doc type at least, if it has a doc type, that tells it that it needs to read the DTDs. The DTDs themselves are a whole series of files. That means if you have 100 DITA files, and each of them references a DTD, which it has to, then you're going to have to read the DTDs, in theory, 100 times. Fortunately, and thankfully, it's not that bad anymore. In the latest version, as far as I can tell, this was introduced in DITA 1.5.1. Elliott Kimber added a patch that caches the DTDs. So the DTDs are read once and they're reused. Unfortunately, that's right now at a slight price of somewhat more cryptic error messages under certain circumstances. But generally speaking, this is a big performance win. So if there's one takeaway from this talk, the best thing you can probably do right now without any significant effort is just to upgrade your DITA to the latest version and benefit from this patch. So we still though have this design problem. We have the DITA is designed to do things in a series of steps. It involves doing this repeated processing. So there's going to be a limit to how fast we can get the DITA to run. One thing to note on the future roadmap of the DITA, there's been discussion about moving the DITA towards a different model of processing, using one of the new tools for setting up an XML pipeline where one result feeds directly into the next step, and that may save some of this extra processing and might provide further speed-ups, again, hopefully without any individual user having to do anything special other than upgrading. But right now that's still on the roadmap. It's not under development yet. So that's one limitation that the DITA has. Another limitation that the DITA has is that much of the DITA is programmed in a language called Xslt, which I'd imagine you're all familiar with. Xslt, otherwise known as style sheets. They are in a language based in XML that on the one hand is a very high-level language, but on the other hand is far removed from the practicalities of performance, and we're going to discuss that later. About sometimes Xslt doesn't really provide us with the feedback about what's fast and what's slow, nor does it give us an easy way to get fast behavior in many cases. So because the toolkit is written in Xslt, or much of it is written in Xslt, that also provides a sort of a built-in slowdown to the processing speed that is possible for the DITA. Xslt is probably still a good design choice because it is easier to be correct when you don't have to worry about lower level data structures and the correctness of your processing, Xslt is essentially what's called a functional language. It prevents the introduction of certain kinds of errors that are possible in other languages like Java. But again, this is a trade-off. In this particular case, with our particular input, it gives us the ability to write things in perhaps a more direct way at the price of a certain amount of performance. Okay, so those are the two things that I'd identify as being the most important limitations that the DITA is putting on performance. Before we get into detail about various changes and advice and things that you might be able to do to change your processing speed, I want to discuss a little bit the importance of measuring whether a particular change is valuable and actually effective. So I had this theory that since the DITA keeps reading and writing files over and over again, and when you read and write files over and over again, one of the things that has to happen every time you write the file to the disk is you have to wait for the disk to actually get a copy of your files. And disks are much, much, much slower than memory, something like 1,000 times slower than memory. So in particular, I generally work on a laptop. The laptop disk is even slower than regular desktop disks. And I figured that for sure, you know, the DITA, as soon as I start running the DITA on my disk drive light starts flashing like crazy. And that means that I'm really sitting here waiting for the disk. When I'm processing my DITA, that means that I'm just sitting here waiting for these writes to get to the disk. But practically speaking, all of those writes are going into a temporary directory, and I don't really care if they're on disk. If my computer suddenly loses power, and I lose my temporary directory, that's really not going to be such a problem for me. So I don't care to wait for the disk. I don't want to pay the performance penalty of waiting to make sure all that data is safely written. It's not like I'm going to pick up where I left off. And because of that, I figured, why don't I just try to avoid writing it to the disk at all? Well, we need a temporary directory. It's hard to rewrite the DITA to avoid using a temporary directory. So you have major rewrites. So I figured the easiest thing to do was to just set up a RAM disk. A RAM disk is a tool to take some of your memory and use it as a disk. It's gone out of style. It used to be a very popular way of improving performance. Practically speaking, these days, it's not nearly as important because the standard cases where it's most useful is to make sure that reads and writes are faster. Usually a modern operating system like Windows or a Mac or what have you will make sure to hide most of that from you by saving as much temporarily in memory and then later sending it to the disk or reading from disk and keeping it in memory for later reads. So if you've just written something to a temporary file, it'll get read from memory, and generally the operating system is going to hide all this from you. It's very unusual that there's a valid use for a RAM disk these days. But I figured that in this particular case, maybe it would be worth it. Because after all, I'm just sitting here watching my disk light flashing. So I tried it. And I ran the DITA 20 times with the same data, once with writing everything to the hard disk and once with writing everything to memory. I used a map that wasn't that complicated, but complicated enough. It had most of the standard features that everybody uses in DITA, and I ran it 20 times back to back in each case. And basically my instinct was wrong, which is to say, I was right that it was faster, But I thought that it would be a significant performance gain, and it wasn't. In this particular run, I found that the average run with the disk was 41.1 seconds. With the RAM disk, it was 39.1 seconds. So the moral of this particular case study is just to show that you might have some intuition about something that might help your data, but maybe it's not significant or maybe it's wrong. If you actually test it, then you can have guidance about whether this kind of change is worth it. On the one hand, I wouldn't recommend a RAM disk for most people. It's an annoyance to set it up, and it has to have, you have to set it up to make sure that it's set up on every boot and so on and so forth, and you have to modify configuration files. For most people, it wouldn't be worth it, but here we can see that it saved 5% of my processing time. So for some people, 5% is very valuable. For some people, it doesn't matter at all. So if you measure, you have guidance to be able to figure out whether you want to invest in this particular change. I should note that despite the fact that I ran it 20 times, I'm none too sure that these averages are particularly reliable. I don't know that 20 times was enough for these particular cases. I had subsequent runs where I was just running it to test other things for this presentation, and I was getting a standard 36 seconds for the version in memory. So I'm not 100% sure these numbers are exactly reliable, but it does reflect what I remember from previous runs when I tried this before, that it was about a 5% speed up in previous attempts as well. So take the numbers with a grain of salt. I think the point still stands. Okay, so now let's talk first about hardware issues. How can the hardware affect your performance? Practically speaking, the DITA OT is going to run on a real-life computer, sitting somewhere, plugged into the wall, or running on a battery, what have you. And it's worth noting that hardware can make a big difference. In contrast to my previous slide, I'm going to give you a little bit of anecdotal information. It's not necessarily proving anything, but I've had, at least we have one client where I have some style sheets that we've developed on my laptop. And my laptop is not a particularly fast laptop. And we run the same data set on the laptop and on a server. On the client server, running this same project, the same style sheets, takes something like 10 minutes. On the laptop, it takes 1.5 minutes. So it's worth noting that having hardware that is devoted to the DITA OT can make a big difference. 10 minutes provides for a much different workflow than 1.5 minutes. 1.5 minutes, you can sit there and wait. You can, I don't know, check your email, respond to an email, and get a coffee or something. If you're 10 minutes, that's already a trip to the water cooler and back, and you've lost your flow. So it's worth figuring out a way to get hardware that can run the DITA OT quickly. And when I say that, I mean quickly for your specific data, for your specific style sheets, the realistic scenarios that matter for you. So the DITA OT is actually doing a lot of processing. It's worth using a machine that's capable of reasonable performance. But when I say that, again, I give the same caveat that I keep giving, that you have to measure and see what's fast for you. But a modern low-end $250 Dell desktop is about as fast as my laptop. And if that $250 Dell desktop was going to move this client's data to 1.5 minutes instead of 10 minutes, that's probably a worthwhile investment if you consider that all of the writers are being paid to sit there and wait for their output. it's the sort of investment that will pay for itself very quickly. So in many cases, if somebody just happens to be using an old computer that really isn't capable of running the DITA OT, it's worth investing in some cheap new computer. It doesn't have to be a fancy high-end server. The DITA OT is not really capable of taking advantage of the performance available in a very high-end server. But again, this is worth measuring. It depends on each particular client. Most people probably have the DITA OT running on hardware that is adequate, but it depends. So one thing to keep in mind is to be sure that the hardware is enough. The particular guidance I would give about hardware is to make sure that there is at least one core, one processor core free to run the DITA OT when it needs to run. Which is to say, if you have a server that's really high powered, but it's busy, so then it's going to be slow. So if you have a fancy high powered 8-core server, then if 7 cores are busy with other stuff and you just have 1 core free for the DITA OT, that's all the DITA OT is really going to want to use. It's not really capable of running in parallel yet. And that means that I should say the caveat, to the best of my knowledge, in theory, ANT could be configured to run things in parallel. In practice, I don't think it works. So practically speaking, just make sure you have one processor free when you actually want to run the DITA OT. My laptop happens to be dual core. That means that I can run the DITA OT and I can browse the web, and it's not going to affect how long the DITA OT takes to run. If you're running it on your laptop, just, dual core is probably the way to go, but it's almost a standard feature nowadays. Again, I'm just trying to advise you not to use bottom and old hardware, the computer that you were throwing away anyway. But anything better than that should probably be good enough. That being said, I've seen in the real world that people actually have hardware that isn't adequate for the purpose. So it's worth making sure that there's a server that has a processor free to run the DITA OT. The next issue to talk about is to make sure there's enough memory. How much is enough? I have no idea. It depends on your workload, and it depends on everything from the number of topics to the size of the topics to the number of conrefs to the number of key refs to the number of topic refs to the size of the rel tables. All of the different factors that go into the data that you're giving to the DITA OT affect how much memory is needed. I don't have any particular guidance. But you should notice a big difference if there's not enough. If there really isn't enough memory, it'll simply fail. So this again just basically requires testing to see if you have enough memory. Some types of processing require large amounts of memory, more than you can get on a standard 32-bit machine for those large workloads. And this, when I say roughly, I mean completely roughly. Again, this is completely varies with input data and size and so on and so forth. But very roughly, if you have more than 600 pages or 1,000 topics, it's probably worth getting a 64-bit machine that runs a 64-bit version of Java. And just to note that Elliot Kimber is currently working on another patch to just set up that copy of Java with the right parameters for the OT, and it'll probably make it as a standard feature in the next version of the DITA OT. But in the meantime, if you're going to go out tomorrow and start running your DITA OT on a 64-bit machine for the next brief period of time till DITA 1.5.2 comes out, it's worth contacting Elliot. Okay, so how much is enough memory? So there are two ways to look at that question. One is, how much memory do you let Java use? And the other is, how much memory is there really on the machine? So most computers that people use these days are configured with virtual memory. What that means is your computer tells all the programs running on it that there is more memory than your computer really has. And what it does is if your programs use more memory than is really there, it'll write some of that stuff that's supposed to be in memory to disk. And it'll move things back and forth between memory and disk in order to enable your programs to think that all of the data is really there in memory. So the symptom of not having enough physical memory, but still having your program run, is something called thrashing. What happens is suddenly your disk drive goes crazy, everything gets really slow. What's happening is your operating system is working very hard to keep up the false pretense that there is enough memory. Every time your program asks for a little bit more memory, it's going to throw something else out onto the disk and pull some data that was already written to disk previously back into memory, and it'll keep juggling between disk and memory. But again, since the disk is 1,000 times slower than memory, this makes things 1,000 times slower. So, I mean, it might not be that bad because practically speaking, it's not going to have, some things will already be in memory and they'll stay in memory. Not everything is going to get swapped back and forth between your memory and your disk. But when this juggling happens and your computer slows down tremendously, that's called thrashing. And you can see, you hear the disk drive working very hard, and you see a lot of disk lights flashing, and everything gets real slow. So that is basically your best symptom for discovering that you have too little real memory. The DITA OT does not necessarily require huge amounts of memory. Again, a standard machine that you buy from Dell is probably going to have enough memory, but it's certainly possible if you have a lot of other things running on the server, or you have an old machine, or you have a machine that for whatever reason was configured with too little memory. So it's certainly possible to run into this issue. So in this case, clearly the cheapest thing to do is to go, the cheapest and quickest thing to do is just to go and add memory. It's not worth spending development time to avoid this issue. It's, you know, an extra couple of gigabytes of memory is going to be measured in the same price as an hour of the time for the writers. So it's not, it's, if this is an issue, it's clearly worth investing. So the other part of memory is to make sure that Java has enough memory to run the DITA OT. Java is told, or can be told, to limit the amount of memory it uses. In the course of performing this preparing this webinar, I figured I'd actually test and see exactly where the line is, and it turns out that the DITA OT can run with fairly small amounts of memory by modern standards. I had, again, a 100-page document running with something like 128 megabytes of memory, and if you add more, if you let Java have more memory, it doesn't actually help anything. So if you have a number that's large enough that it allows your project to run to completion, you probably don't need to spend too much time fiddling with this parameter. I just set it up to run with successive numbers with this parameter. The parameter is a parameter that is set in an environment variable in int ops. It's usually set when you first start up the DITA OT. You start up by running start command.bat, and one of the things that it sets up is these int parameters that get passed into int, which in turn get passed into Java. One of the parameters is this -xmx. It's a parameter that gets passed onto Java, and it just says you have this much memory. So I try to running through just a series of different values. And it turns out that basically, once you have enough, it doesn't really change your processing time to give it more, or to allow it to take more. I don't know whether this is a universal result. I don't have extensive experience with this. But practically speaking, it appears that it doesn't change things much. The reason why I found this slightly surprising is that Java is known to have a particular behavior. Java does something called garbage collection. When memory is no longer used, it still has to figure out that the memory is available. So it does something called garbage collection. It goes looking for memory that's free so that it can reuse it. So if Java is running low on memory but hasn't run out of memory, then it has to run garbage collection very frequently to just make sure there's enough free space. So I kind of expected that there would be a threshold where Java would run garbage collection very frequently and would pay a significant performance penalty. I didn't find that in my testing. I'm suspecting that that's because the DITA doesn't actually free up so much memory as it's processing. I'm not entirely sure, but practically speaking, it doesn't seem to have much of an effect, but certainly it won't have an effect if you give it plenty of memory. So even though tweaking your memory settings might seem like an easy fix, it doesn't seem to be. Okay, so that was basically what I found in general in terms of giving Java enough memory. Now, there are issues with memory. One of the things to note with memory is that people run out of memory and they're stuck on a particular computer. They have a 32-bit machine. It really needs all of the memory that they have available. They can't add memory. They're up a creek. So they ask on the DITA users mailing list, they ask, what do you suggest we do? And the standard answer is usually to set reload style sheets equals true. There's an ant parameter that you can use to set this. You don't actually have to go recoding all of your build files. You can just set this as a parameter when you start up the DITA. What this does is it rereads your style sheets for every time they are run. That means if you're going to run your conref style sheet on 100 different DITA files, then it'll read the conref style sheet 100 times instead of the one time that it does right now. So that's slow, and we've been talking about improving performance, not making it worse. So you don't really want to have to set this parameter. It is ideal not to get into that situation. But sometimes, you're out of memory, and the standard advice is then to set reload style sheets to be true. So it's much better, if possible, to figure out how to give the DITA more memory if you can. So we discussed basically the easiest thing to do in theory is to upgrade your machine. If you really have large data sets, make sure you have a 64-bit machine. They're not quite standard these days, but they're becoming standard. It's not so far out to get one that they're not, super fancy, expensive servers. They're just, it's not the 250 Dell, but it might be the, $450 Dell. So just one piece of advice before you give up and buy a new machine is that we did have one customer who solved their memory issues by switching their version of Java. The standard version of Java that you download comes from Sun Microsystems, which has now been bought by Oracle. Back in the day before they were bought, so Oracle also had a different version of Java, and they still provide it for free. Called JRocket, and JRocket, for this customer at least, solved the memory problems. It apparently is somewhat more efficient with memory. It's essentially supposed to be a drop-in replacement for Java. I haven't personally installed it, so I can't tell you how complicated the installation is, but it's got the exact same utilities that standard Java has, and the way you run it is the same. It's basically you're installing a different copy of Java from a different company. I'm sorry, I just noticed now that I've been having audio issues. Scott says, has it improved or gotten any worse now? I'm going to try one thing to see if I can improve matters. Is that any better? Okay, I hope that that will improve matters. Okay. So just to review before we move on to talking about style sheet performance, we discussed the importance of measuring performance using your own data and trying to figure out using what works for you. We discussed the fact that you don't need great hardware to run the DITA OT, but you do need decent hardware, which is to say probably just about anything modern. We discussed the importance of having enough real physical memory on the machine. We discussed that having extra memory over and above whatever happens to be needed for your particular data set is probably not going to be of so much value. And we discussed that it probably won't be of so much value to tune the memory parameters so precisely. Once you have a working copy of the DITA OT with working parameters, you're probably set. It's not going to change your processing time from 10 minutes down to 1 minute by fiddling with these settings. Okay. Oops. Okay, so once we've discussed the and of course the key point of review is to make sure that you upgrade to the latest DITA 1.5.1 with Elliott Kimber's patch to make sure that you don't keep rereading DTDs. Okay, after that point, we're going to discuss Xslt Performance. When you're writing style sheets, it's not necessarily evident when you write a particular style sheet what the performance consequences will be. And part of the reason for that is that unlike, say, a language like C, where what actually happens behind the scenes is very closely related to what you write, Xslt, you can write one-liners that are fast and one-liners that are very slow. It's in part a testimony to the power of the language that enables you to write complicated expressions just in one line. But in part, it's just simply a challenge because you still want reasonable performance, so you have to be pretty careful about what it is you write on your one line. So when we're talking about style sheet performance, I think that it's not necessarily so practical to go ahead and try to look at all of the different style sheets in the DITA OT and to try to fix all of them up. If you have the opportunity to do that, that's great. Usually speaking, the standard out-of-the-box style sheets have reasonable performance. Not always the case. So sometimes there might be a bug in the style sheets that is worth fixing, and if you find one, it's worth reporting so that everybody else can benefit. If you have any bugs or patches, please report them on SourceForge. If you go to the DITA OT project on SourceForge, there's a tracker and you can just file bugs. But most users of the DITA OT do make some customizations to the DITA OT, and when you're writing your customizations, it's worth being aware of the performance consequences of what you write. So we're going to talk about Xslt Performance, about style sheet performance, and we're going to talk about the kinds of things that you should write and should be careful not to write. We're not going to be able to go into great detail in the time that we have, but we want to at least cover the basics. So when you write a style sheet and you're developing, you may not think about exactly what has to happen behind the scenes for your style sheet processor to actually do what you ask. So here's an example. If you have a variable, I'm just setting a variable for instance, and we have a very simple Xpath here. You have a select, you select any node where the ID attribute of that node equals a variable that you already have from before called ref ID. So it's worth realizing what that actually has to do is it has to search through your entire document. That means every single element in your document, no matter how many there are, it's going to have to check and see if it has an ID, each one of those if it has an ID attribute, and for each of them check and see if the ID attribute is the same as whatever's in your ref ID variable. So when you write something like that, you have to be aware that you're actually doing a search over the entire document. That's fine if that's what you want to do, but if that's not what you really mean, then you could write it more efficiently. For instance, let's say you already know that for whatever reason, in the particular example that you're working with, you know that it's going to be in the same topic or in the same particular part of the tree. You may be able to give it more guidance about where to look. For instance, if you know that it's going to be another element that is a descendant of the parent of the current element. So you can actually specify that in Xpath. You can say, in this particular example, just adding 2 dots will now restrict the search. Instead of searching through the whole document, you're just going to search through this particular part of the document. So it's worth thinking about what kind of search you actually need to do versus what kind of search you're actually writing. In both cases, let's say the IDs happen to be unique. So then you're going to get the same result in both cases. But if you could write the faster one, then you'll want to write the faster one and you'll get better performance. So it's worth making sure that when you write, you consider what's going on. If you, in particular, that / that appears in this example is something to watch out for. / always means you're searching through an entire document. And if you do this somewhere in some piece of code that gets repeated very frequently, so that could be slow. And / is generally not needed. It is rare that you actually need to search through the entire document. So it's worth making sure when you're writing these one-line expressions that you know exactly how much computation is happening out behind the scenes, and try to avoid doing extra computation. Usually you can just sort of figure it out. You can figure out what kind of computation would have to happen in order to check your expression. Now, just getting back to the caveat I keep making about measurement, in theory, your style sheet processor could optimize this, and it could make the first search extremely fast. In theory, you could have a case where the DTD declares that the ID attribute is an ID, and if it does, then the XML specification requires that it be unique. And if you know that it's unique, then the style sheet processor, in theory, could take advantage of that and therefore have an optimized search that takes care of it. And that's all true. So practically speaking, it won't be true. Practically speaking, when we're running these style sheets, we're all using Xslt, which does have some optimizations, but as far as I know, not that one. But it's worth measuring to see exactly how fast things actually run, because practically speaking, even if you know that some computation is more complicated than some other computation, it could very well be that some things are optimized, some things are not, and it's therefore not always evident what's going to be fast and what will be slow. It's always worth measuring. Of course, there is, as I'm trying to do here, there is some basic guidance that if you express simpler computation, hopefully your style sheets will be faster. In almost all cases, if you express much simpler computation, you're going to get significant speed up. On the note about optimization, that sometimes the style sheet processor might be able to do things behind the scenes to make things faster. So Xslt, which is basically the only thing everyone is using, comes in multiple versions. It comes in a free version that we're using that's distributed with the toolkit. It also comes with commercial versions. The commercial versions do have some additional optimizations. Whether it actually makes a performance difference for you, I couldn't tell you. It depends on your data, and you'd have to measure it. In fact, the commercial versions of Xslt are not that expensive, so it's worth considering as a possible way of speeding up your performance. The commercial version does come with Oxygen, among with other tools, so it's possible you may even have a copy that you can use for testing at least. You probably want to get another license for the server, but it's, the last time I checked it was 200, I forget, $200, 200 euros, something. It wasn't a huge investment, so if it happens to matter, it might be one way to speed up performance. That's basically a side note here. I'm right now focusing mostly on performance of style sheets, and the one takeaway that we had so far with style sheet performance is, well, two takeaways. One is watch out for things that start with // and two is be aware that what you write in one line might be slow. So one way of figuring out what's slow is to use profiling. This is basically out of scope of my talk right now. It's generally a good idea to be able to measure and figure out where in your style sheets things are slow. There are many commercial tools. Oxygen provides profiling. Stylus Studio provides profiling. Fancier versions of Visual Studio provide profiling for Xslt. I think that may only be for Xslt version 1, and now you can start using version 2 in your style sheets, given that the latest version of the DITA OT should fully support Xslt 2. So you can run the style sheets if you set it up correctly in any of these tools, and it'll tell you which are your pain points. It'll tell you where in the style sheets you're doing something that's slow. This might be overkill, though. In a lot of cases, when you're making a small change, you're going to need that change, and it's just when you're writing it, you should keep in mind what the performance consequences are of the change you're making. And you can often just eyeball it and figure out whether you're doing something fast or slow. So if you happen to have an evident pain point like that double slash, then it's worth fixing. Often enough, it's simple enough to fix, and even if it's not going to be your main pain point, it might be easier than fixing some of the more complicated parts of your style sheet. So it's worth keeping in mind. For many people, it would be very much worthwhile, particularly if you can't figure out where you're losing a lot of speed. But in many cases, you can also eyeball it and find lots of low-hanging fruit. Another example of what happens in just one line of Xpath. This is a bit of a contrived example. It's mostly because I encountered a real-life example that was pretty similar, and I don't remember where it was, so you'll have to bear with me with this contrived example, but occasionally you do run into code that is pretty similar to the following. I have an example here of a one-line Xpath expression. Supposing we want to find out for any given node if it has preceding or we want to collect those preceding siblings that happen to have following siblings that are unordered lists. So in order to take apart that one line, we have to do practically a bunch of different tests. That means for the node that you're on, you have to check each preceding sibling. And then for each one of those, in order to test the next part of the test, you have to test every following sibling. And then for each one of those, you're going to have to run contains. And the contains function is not that fast. Contains, I mean, on the scale we're talking about, it's going to execute in, microseconds, something very fast. But it's not a super fast, single processor instruction type of operation. It has to hunt around inside the class attribute, it has to find the class attribute and hunt around inside the text that's there and look to see whether it has matching text. So it has to check basically every character and see whether there are any characters there that match up with the characters here. And that means it's going to have to hunt through it. And that's not going to be an instantaneous operation behind the scenes. So let's just look at this with some sample numbers. Again, we're talking about one line of code. So if you look at an example where you have a particular case with 100 different nodes, now let's pretend that in these 100 nodes there isn't going to be actually any topic UL, so the test is never going to succeed. And let's run this test, this one line, on all 100 nodes in this sequence. So we could do the math to figure out how much processing this has to do, but it's easier for me to write a program. I apologize, I wrote it in Perl. That's just sort of what I do when I'm trying to do things quickly before a webinar. I hope that it's accurate. I didn't necessarily have a good chance to test this carefully to make sure that the reasoning is correct, but I'll just explain it orally, and if anybody notices any problems with my reasoning, please let me know. So for each one of our 100 nodes, we're going to have a loop. For each one of those nodes, we're going to look at each one of the preceding nodes. And for each one of those, we're going to look at each one of the following nodes. And for each one of those, we're going to call contains. So let's just count that. How many times do we call contains? So this Perl program, if I run it, tells us that there are 333,000 calls to contains with our sample of 100 nodes. So it's worth considering. We just wrote one simple line of Xslt, of Xpath within an Xslt, I don't know, inside a variable value of whatever it is, just inside an expression that in an Xpath. And you might end up doing a lot of computations. So we can provide some general guidance, but it's worth just trying to, in the back of your head, thinking, well, what does this have to do to obey what I tell it? If I tell it to look at every preceding sibling, well, it's going to actually have to do that. It's going to have to check each one of the preceding siblings. And if I tell it next following sibling, it's going to have to check that. And if I tell preceding, well, it's going to have to search through the whole document all the way back to the beginning. So each one of those kinds of operations costs a certain amount of calculation. And if we think about it, even though it all fits in just a line, you can figure out just by staring at it more or less how much computation has to happen. I'm noticing, of course, that I've gotten off by one error in this computation. It should have been looping from b plus 1 to 100, so clearly this number isn't exactly accurate, but the point still stands. Okay, so floating around on the internet, saved a bunch of places. Mike K sent. Mike K is the author of Saxon, so he should really know about how to write efficient Xslt. He's the author, or at least the editor of the Xslt 2 specification. If you want an expert, he's it. So he gave in an email address, in an email message, just a couple of tips about how to write efficient Xslt. I don't necessarily know if this is an authoritative. These are his 8 tips that are the most important, or these were things on the top of his head. One of the places you'll be able to find a copy of this is Dave Pawson has an excellent website. If you search for his name, you should find it. That has a lot of information about Xslt and about XLFO. So if you're writing PDF style sheets, it's a great resource. So one of the things he has here, there is this email from Mike. So he gives 8 tips to write efficient Xslt. So one of which we mentioned already. Avoid repeated use of // means that anywhere that appears, you're going to have to do a search through your entire document for whatever it is you're searching for. And usually you don't need that, so avoid it if possible. Another point is don't evaluate the same node set more than once. Save it in a variable. Generally speaking, variables are your way of saving computation. So if you are going to have to do the same thing many times, if at all possible, try and make sure that ends up in a variable so you only have to do it once. He says avoid Xslt number if you can, for example, by using position. I'll discuss that on the next slide. Use Xslt key, for example, for solving grouping problems. Also discuss that on future slides. Avoid complex patterns and template rules. That means if you have an Xslt template, there's a match attribute, and that match has a pattern that describes what kinds of things in your input will trigger that particular template. So try not to make that too complex. Instead, sometimes you can just match a simpler case, and then if you have a couple of different kinds of processing that you might want to do, and instead of writing them all into different templates, you might be able to get away with using Xslt choose to switch off between the different kinds of processing you would want to do. We'll discuss why on the next slide. You want to be careful when using preceding or preceding sibling, or when using following or using following sibling. We discussed that just a slide ago. This often indicates an algorithm with n squared performance or n cubed or depending on how bad it get, it could be very poor performance. So you want to watch out for that whenever possible. Sometimes you can't. So practically speaking, you want to make sure you get correct output before you get fast output, usually. For most of our customers, the first things first, you want to make sure that you get the output that you want. But once you do that, it's worth thinking about, if you have choices about how to implement something, if you can avoid using these tools, then all the better. He gives another point: don't sort the same node set more than once. If necessary, save it as a result tree fragment and access it using the node set extension function. What that basically, so this is dated. Node set is necessary back if you're using Xslt 1. It's not necessary if you're using Xslt 2. But practically speaking, what the point behind this is very similar to the one we have in point number 2, which is just to say, if you have something that you're going to compute over and over again, save it in a variable. And then the final point that he makes is to output the text value of a simple PC data element, use Xslt value of, and preference Xslt apply templates. It's not necessarily worth elaborating on very much, and it's usually not so helpful in the context of DITA because frequently you don't know what's inside. Value of basically will grab the text. It won't do subsequent processing, so usually you don't know if there's going to be more content inside whatever element you're working on. You usually want to apply templates, even if it's slower. Okay, so just to elaborate on 3 of those points, you want to use Xslt number when it's appropriate. So he advised you not to use it. I'm telling you that most of the cases that you're going to want to use it in the context of DITA, it's probably appropriate. It's a tool like everything else, but Xslt number often is an easier way of numbering things. If you want to number chapters, it's probably the appropriate tool rather than trying to work around it and figure out formatting and so on and so forth. So Xslt number is a tool. There are probably situations where that's good advice. I don't know if they apply to us so often, so my commentary on that particular tip is, for us, we can probably forget about it. Xslt key, I wanted to emphasize that Xslt key is a good idea. We'll discuss what Xslt key is on a future slide. This is probably, Xslt key I think is underused in the PDF style sheets at any rate. This is probably the tool that is we could use to find the low-hanging fruit in speeding up the built-in style sheets. Xslt key is a way of avoiding some of the computation that we had just discussed, and we'll explain exactly what it does in a moment. So I just wanted to encourage you to follow up on that one. So to elaborate on the point about avoiding complex patterns and template rules, realistically, most of the patterns that we use in the DITA OT style sheets are reasonably complex. Every time, more or less every one of the template rules has an expression which starts with a star. That means we're going to try to match any element, and then we're going to look at its class attribute and then do a string, use a string function called contains to look and see whether a particular substring appears in that string. That's just not the most efficient way to use Xslt. Realistically, we can't avoid it. The model that we're using is DITA. We're using DITA with its class attributes, and the reason that the class attribute is designed the way it is to enable specialization. That means that when we write a template, we write it with a star and we look for a particular pattern in the class attribute, so that if you handle topic UL, then your template will also match any specialization of topic UL. And that means that your style sheets will do the right thing even for new elements. They don't have to know about them in advance, because the DTDs are going to fill in the class attribute with the right information. That means that your style sheets will handle specializations without any further work. So we can't avoid having complex patterns in our template rules. But it's worth considering why he gave that advice. Whenever you call XSL apply templates, what that does is it takes all of the child nodes of the current node, and then for each of them, it tries to find the appropriate template. And the way it's going to do that is it's going to take all the templates that you have in all of your style sheets, and it's going to match each one of the patterns until it finds one that matches. So that means that if you're doing complicated computation in your match, then every time that particular match is tested, you're going to have to pay that price. So if you have a very complicated and slow test in one of your match attributes, and it runs, it's a little bit complicated to figure out what sequence the Saxon is going to decide to test the different template patterns. But practically speaking, if it happens to test it before it finds the right template, so it's going to have to run that computation on everything that comes through. So you want to avoid complex computation just to make sure that this way of finding the right template runs quickly. So we might be able to do a little bit about that. That means that if we have something that's really complicated, we might be able to speed things up by using the advice that he gave. Sometimes we can match just some particular general case, and then within our template, we can handle the different subcases using Xslt choose. Or as an alternative, sometimes we know that we're going to have to do some extra testing, so we can use a moded template. Moded templates are just a way of dividing up your templates into different groups. You've probably seen it if you've looked at the style sheets long enough. It shows up in a number of places, many places in the style sheets. Modes basically say, okay, well now we'll run we'll run through the different templates only in this subset that appears in the with this mode. So one way to handle this particular case is if you actually really need a case like this, you can go ahead and find a match, and then after that match you can go ahead and run an apply templates for within a mode to find the subcategory that you're looking for. Okay. So what is this Xslt key that we've been talking about? An Xslt key, well, maybe easiest to explain with an example. Somewhere on the top level of the style sheet, you can define a key. So here's a particular example of a key. The key has a name. In this case, the name is map topics. It has a pattern. The match is, going to figure, the key is going to be defined for every node that matches the match pattern. So in this case, it'll be any element that's anywhere under open topic : map. And the value of the key, I'm sorry, not the value. I forgot the jargon. I'm sorry. The key itself, the value that you'll use to look up something that is going to be stored in the key is going to be the ID attribute of each node. What this is going to allow us to do later is to use, let's say we have an ID, we can ask the key, well, we can ask the map topics key to return those elements that have a particular ID. So later in your style sheets, you can look up items with that key. You want to find anything, any one of those nodes anywhere under OpenTopic Map and you want to find them by their ID, instead of searching through all of those elements again and looking at their attributes, it's already going to be stored in the key. Key should be implemented efficiently, hopefully with a hash table. I'm not 100% sure what happens behind the scenes. It certainly is faster. You basically just pass it the name of your key and you pass it the value that you want to find, and it'll return that node. So this key map topics ID is equivalent to searching for, I thought I had typed this in actually, I guess not. It's equivalent to searching through OpenTopic Map for every element that has an ID that equals the current value of $ID. But it's faster. And frequently enough in our style sheets, we want to be able to look things up by a particular attribute or by a particular computation, and this allows us to define in advance at the top level, say we're going to need to look these particular elements up, and because we're going to need to be able to do this lookup later, do the computation in advance, and then we'll have a quick way of doing finding a reference later. So this lets you basically do the search through OpenTopic Map once instead of many times. And note that this particular example I cut and pasted from something that someone had done for one of our clients. It's a piece of code that was part of a change to their table of contents handling. That particular change, we're going to discuss in a moment the other part of this particular change, but had something like a 40% speed up in generating their table of contents in a large book, and it cut their processing. In this particular case, it was a huge book, and it was processing for 2 hours or something, and they eventually shaved off an hour of processing. And this is despite the fact that this is not following some of the advice I just gave. It uses // so it's searching through your entire document for OpenTopic Map. That being said, when you're doing this, you're only doing it once. If you'd put this without a key and you had your select search for OpenTopic Map and then look for any elements with that particular ID, every time you ran this particular Xpath, you would be searching your whole document. So here, because you pay the price only once, it's not so bad. We were still able to gain huge speedups because this is something that only gets run once. Now, the correct way to write it, of course, OpenTopic Map is one level down, so that means that I'm pretty sure that I got that right. The one level is that it is one level down. And practically speaking, then, if you'd done a /*/OpenTopic Map, that would have found OpenTopic Map much more quickly and would not have searched through the entire document. So you could have expressed the same thing with the guidance that we had discussed before in a much simpler way, in a way that is not any more complicated and is much more efficient. Despite that, keys are still a big win. Okay, another example of something that might realistically appear in your code that would make things slow. When you do computation, if you do something inside a loop, that means it has to run every time you go through the loop. If you do something inside a template, so maybe you don't think of it as a loop, but if you have a template that runs for every paragraph, that code is going to run for every paragraph that you have in your document, and that could be hundreds or thousands of times. So practically speaking, inside a template, for most templates that we have, that's inside a loop. If you have computation that you could do once, but you do it inside a loop, and you do it many times, it's going to slow you down. And it's a price that you don't have to pay. if you happen to know that you have a computation that is going to stay the same, that it's not context sensitive, it doesn't need to be calculated relative to your current node, then you can just go ahead and do the calculation in a top-level variable. This is sort of counter to your standard advice with most programming languages. You generally want to avoid defining global variables. In the case of Xslt, global variables can be very helpful, because global variables are things that are not going to be running inside a loop. So to give this example, a specific example, if you have a variable that just stores all of your topic graphs that appear in your document, and you set that variable with // contains class map topic graph. So you're going to search through your document for every element that happens to be a topic graph, and then you'll set your variable to be equal to that set of topic graphs. So you're generally not going to want to do this exact computation just because for the same reason we keep discussing, you generally want to avoid searching through your whole document. So // is generally a bad idea. The one thing you notice as soon as you look at this is that this does not in any way depend on the current template, the current node. This variable can be defined once. So because it only needs to be defined once, and it can have the same value every time, why not pay the price of setting it up only once? So if this appears in a template, you want to move that variable out of the template, make it a global variable, and basically with the two changes here of moving variables that involve a lot of computation out of the template, and the key that we discussed on the previous slide, we have one customer who shaved, I think, 40. I may have contradicted myself, but I'm pretty sure it was 40% over their entire processing of their book just by making these simple changes on one template. So it's worth watching out for slow computation, and if you're going to do slow computation, at least only do it once. Don't do it many times. Before we finish, just a couple of quick tips. One of them is that basically, aside from the general performance issues, PDF style sheet developers have a particular issue with performance, which is that frequently you're going to be tinkering with your style sheets, and you're going to want to make a couple of small changes, and you want to see how it looks. That may mean that you're going to run the same data over and over and over again. So the DITA OT, if the cycle is even a minute or two, might very well slow down your work cycle. So there are just two quick pointers. The first quick pointer is that you should try to make sure that your style sheets save your topic.fo file if you're making PDFs. Topic.fo is the file that is going to be processed to make your PDF. There are tools. Every one of the different tools have a way of viewing this. For instance, Antenna House has a graphical interface called Xslt Formatter, or AH Formatter, depending on which version you have. You can open up the topic.fo file, and you basically hit F5, and it'll just refresh. So because of that, practically the fastest way to test to see whether a tweak in a particular bit of formatting is going to look the way you want, the fastest thing to do is to take your final topic.fo file, just edit it directly, and then look and see if it appears the way you want it to appear. Don't even bother running the DITA OT. So it's not of general value for most people, but for style sheet developers, this is a valuable tip just because you can test a whole series of tweaks very quickly. And then once you get it looking exactly how you want it to, you can then go and figure out how to get these changes to work in your style sheet. So if you discover that you need to tweak, the exact distance between a border or turn a border on or off on a cell or in a table or what have you, it may be easiest to experiment in topic FO and avoid waiting for the DITA OT. The second piece of advice is that you can configure the toolkit to have another ANT target, which enables you to run your DITA OT once to produce a PDF like normal. And then once you've done that, you have temporary files that are sitting in your temporary directory. And those temporary files are not going to change if you change your PDF, your final PDF style sheet. All the conrefs will be processed the same way. All the metadata is going to be processed the same way. So the only change you're going to need to make is to your PDF style sheets. Well, you don't really want to do all the pre-processing over and over again. So you can set up your toolkit to pick up from those same temporary files and keep running. So given that you can do that, you can skip the earlier processing and just run the last part of the processing. Sometimes it's a good way of tinkering also with your PDF style sheets. Again, it's not of any use for standard DITA. You're going to want, this is only talking about when you're running the same DITA content over and over again and tinkering with your PDF style sheets. But practically speaking, it's a useful tool to have in your toolbox to be able to do your development faster. If anybody is interested in this, we don't have it prepackaged. It's, you know, a couple of lines that have to be kind of pasted into different places. We don't have it as a plugin, even though really one of these days it should be. So if anybody has a use for that particular tool, give us a call, contact us, email us.